already know, right? The output from the microcontroller, right? You can drive LED, right? So you can light up an LED, right? But as we have discussed earlier, right? For LED to light up, right, we only need 3 milliamp current, right? 3 milliamp. So which is a very small current. So if you want to drive a bigger load, right? For example, like you want to drive a motors, right? Washing machine motors, right? That requires a much bigger current, right? So how do you drive those motors, right? Or heaters, etc., right? So in order to drive the much bigger loads, right? You need additional components, right? To supply the bigger currents. The outputs from the microcontroller alone, right, is not sufficient, right, to drive the bigger loads. Alright? So what are the methods we can drive bigger loads, right? We will discuss, we will use different transistors, for example, like bipolar transistors, MOSFETs, or H-bricks. This one we will discuss later. And also, we are going to discuss the outputs, right? So earlier we say we only use the digital outputs, right, which is only 0 or 1. But if we want to have some value in between, some precise voltage values, right? So how can we do that, right? So we can use DACs, or we can use the method called pulse width modulation. We are going to discuss in more details on this part. Okay, and also we are going to discuss some of the motors, like servos and motors. Right? So this is actually one of the main components we are going to drive. Is it right? Almost in all the appliances you will see, right? Washing machine, heaters, or your cars, whatever, right? You need to drive motors, right? As a mechanical engineer, right? Motors actually, I would say, is one of the most important components you are going to deal with, right? So how do you control motors? How do you control the movement of motors, right? Which is actually a very important topic for you, right? Right? Yeah. Okay. So how to drive the load, right? So again, you can see the notes here is somewhat outdated, right? So we still mention the PIC, but anyway, this is almost the same as our Arduino. Okay, the concept is the same, right? So the output from the Arduino, right, we can only supply a few milliamp current, a few milliamp only, right? 3 to 5 milliamps, right? So if you want to drive, if you want to have a much larger current, right, you need additional components. For example, like you can use bipolar transistors. Anyone you learned bipolar transistors before? Yeah, I know we have discussed the what's that, diodes, right? So have you learned any transistors before? Bipolar transistors, MOSFET transistors.
We have studied, yeah.
Zero.
Sunday, yeah.
What's that? Sorry? So it's one of the NPN.
One is studied.
MOSFET. Oh, okay. Yeah. MOSFET, yeah, indeed. MOSFET is one of the most popular transistors, right? Transistor actually you can use what? You can use for your amplification, right? Or you can use it for your if you want to have a bigger current. Yeah. Okay. So let me go through what is the bipolar transistors, right? You know, bipolars, right? Bipolars, we have two common bipolars. One is called NPN, one is called PNP bipolar. One is called NPN, one is called PNP. Right? So from the name here, right, actually you can see, for the NPN, right, basically it's like you have two diodes, right? One is N, P, N, right? Okay. So you have two diodes, right? Diodes basically is one PN, right? PN junction is a diode, right? So NPN basically you have two diodes inside here, which plays back to back. Okay. And for bipolars, right, actually it's three terminal device, right? So this terminal we call it base terminal, right? And this terminal we call it collector, and this terminal we call it emitter. Right? Okay, so let's go back to the emitter. So this is collector. So collector. Right. This is the base. Okay, so this is the three terminal device. So PNP is the same, right? You have P and P. So one of the things you need to remember is, if you look at your base emitter, right? So this junction, so you can see a diode, right? So you know, for PNP, right? For the circuit symbol, you have this one. Right? So this is the symbol you are going to use in the circuit. Right? So again, here is base, here is collector, and here is the emitter. Okay. So if you look at your base and emitter, right, this actually is a diode, and you need about 0.7 volts, right, to turn on. Okay, turn on is this junction. Okay, and if you look at the current, right, so you will have this. So the current here is what we call is a base current, like IB. Right? The current here is we call it collector current IC, right? So you have roughly this kind of relationship, which is beta IB. Right? Okay. So if you check any data sheet, right, you will see the value for the beta. So beta actually is the current amplification. So basically, the current from the base, right, it will be amplified by this bipolar transistor. So beta is in the range of 100, about 100, right, for a typical NPN transistors. Okay, so this is the basic idea, right? So for example, right, let's say your base is connected to your Arduino outputs, right? Okay, Arduino outputs. Okay, so we have discussed the output current from Arduino I/O pins, right, can only be about 3 milliamps, right? So if this current goes into your base, right? Okay, so because of the amplification here, right? So your current here can be 100 times of the 3 milliamps, right? So it can be 300 milliamps, right? So that's the rough idea, right? Okay, so if you connect to your the base to the digital I/Os from the Arduino, right? So the current can actually be amplified by transistors. So you can use this current, right, to control the supply to motors, inverters, etc. Okay, yeah. That's the idea for bipolar. Okay, so in the notes, yeah, you also have these circuit symbols, right, for the NPN. Yeah. Okay, so you need about so if your emitter here, right, is grounded, right, 0 volts. So you need about 0.7 volts at the base in order to turn on this transistor. Okay. And the current here, IC equals beta times IB. So beta is the amplification. Right? So typically, actually, it's in the range of 100, 50 to 100, depends on the kind of transistor you're going to use. Okay. So for the PNP, actually, is somewhat similar. Okay, so now, if you want to drive a load, right, which is roughly up to 500 milliamp, right? So what you can do is you connect your NPN here, your load will be here, right? Okay. So the current now from the collector, right, from your bipolar, actually is flowing through your load here. Okay. So your output from the microcontroller you connect to your base. Okay. So output current from the microcontroller, yeah, is very small. It's only 3 to 5 milliamps. Right? It goes into the base, right? Because of the current amplification, right? You can supply roughly about 500 milliamps, right, to the load. So that gives you the idea. Is it clear so far? Yeah. So basically the idea now here is if you want to drive a much bigger current, right, so you need additional transistors. So your output from the microcontroller, right, so you connect to the base, right? So now the current from the transistor, right, can be used to drive the load. Okay, now this is actually a Darlington pair. Right? Basically, it's a variation. It's a combination. You use two bipolar transistors, right, to drive even larger current. Right. So if you look at the Darlington pair, right, basically you have two NPN transistors. Right? Two NPN transistors. Right? So how it works is, okay. So a few things, right. So again, our output is from microcontroller, right? So we connect to here. So now you see there are two NPN here. So if I ask you, right, how much voltage I need to turn on this Darlington pair? So you can see actually you have two diodes right here, right? From here to here is one diode. From here to here is the other diode, right? Right. So basically you need 2.7 volts, right? Turn on this Darlington pair. So you need 1.4 volts here, about 1.4 volts here to turn on this Darlington pair. Then why this Darlington pair, right, can supply much higher current? So show you. Okay, so you have a Darlington pair, right? Okay, two NPN transistors. Right. So you see the interesting part is sorry. The current from the first NPN, right, it becomes the base current of the second NPN transistor. So you see the point, right? So let's say you have an IB here, right? So the current here actually is about beta times IB, right? Right. But this beta times IB actually is the base current of these transistors. So then what is the output current here? So the output current actually is a beta times beta, right? Beta squared IB, right? Which is sorry. sorry. What is the question?
No.
Huh?
I know.
Okay. So the current actually is this one. Yeah. So you can see the current, right, is being amplified by beta squared. Right? So if the beta is 100, right? So the terminal pair actually you can amplify the current by 100 squared is 10,000 times. Right? Okay. Okay, so terminal pair is a very commonly used configuration. So if you want very big currents. Okay, next. Okay, some of you mentioned this MOSFET, right? Yeah, indeed, MOSFET is another very common component, right, used for the to drive the bigger loads, right? So can I ask you? So if you look at the MOSFET, so this is the circuit symbol, right, for the MOSFETs. So MOSFETs again is a 3-terminal device. Right? So MOSFET it has a drain, gate, and source, right? So this is different from bipolar. Bipolar we have collector, base, and emitter. Right? So MOSFET we have drain, gate, and source. Okay. So again, the output from a microcontroller, right, is connected to the terminal somewhere in between here, which is the gate terminal. Okay. So the difference between the MOSFET and bipolar is, so for the bipolar, we say the base current, right, is a very small value, right? But anyone can tell me, right, what is the current at the gate terminal for MOSFET transistors? Huh? Is there any current here for MOSFET transistors? Yeah. Okay, so for MOSFET transistor, right, the gate actually don't have any current. Right? Okay, so the gate here only take in the voltage. Right? So for the MOSFET, right, the operation actually even simpler. Right? You can view the MOSFET, right, as a switch. As a switch, as a so you have a MOSFET here, right?
MOSFET. Very fair.
Okay. So we have the drain, we have gate, and we have source, right? So the current flow through the MOSFET, right, actually is controlled by the gate, right? It's the VGS, right, which controls the current flow. Okay. So the voltage here, right, it actually is like you can view it as like a water tank. You turn on the water tank, the current flow. You turn off the water tank, right? The water, the current not flow, right? Okay. So the operation for MOSFET is actually simpler, right? Compared to the bipolar transistor. And the current actually is a function of VGS, right? So if you have a larger voltage, right, and gate, right, you will have larger current. Again, how much current you can actually get, you need to look at the data sheet for the particular MOSFET you are going to use. Right? Okay. But anyway, the amount of current, right, for MOSFETs depends on the voltage you are going to subscribe to gate. Okay. That's the idea for MOSFET. And to turn off the MOSFET, right, there is a voltage called threshold voltage. Right? So basically, your gate voltage, right, need to be above the threshold voltage, right? So the MOSFET can be turned on. Right? So the threshold voltage, right, the typical threshold voltage is also around 0.6, 0.7. Right? So this number you just remember, because for the diode, right, we say the terminal voltage is 0.7 volts, right? For most of the MOSFETs, right, the threshold voltage also around 0.6, 0.7 volts. Right? So you can see that these are magic number, right? 0.6 or 0.7. So to turn on transistors. For bipolar or for MOSFET, yeah, they need around similar amount of voltage to make on. Okay? Okay, so the other one is we want to discuss is you need to be careful, right, with the inductive load, right? So if your load, right, has some inductive components, right, this part you need to be careful because for the inductor, right, you know, anyone learned the electromagnetic before, the electromagnetic induction. So that means when your current change, right, when your magnetic field change, right, your current actually change, it will induce the. Yeah, anyone has learned this before? The Faraday induction and those things, no? Huh? Faraday induction, Ampere's law, whatever. Yeah, it's alright. So basically, for the inductive components, right, when you switch off the current, right, the inductive component which you want to keep the current, they have a tendency, right, to oppose the change of the current. So which means is if you want to switch off the current, right, at some point of time, right, this voltage can be higher than VDD, right, because of the inductor. So basically, you want to protect your device by using a diode here. So let me ask you a question here, right? So if you have a diode here, right? If you have a diode here, what is the maximum voltage you can go for this point? What is the maximum voltage you can have here? Okay, so you have a PNP here, you have a load here, right? Yeah. Here is your VDD, right? So we put a diode here, right? Connect to this point, right? So my question to you is, what is the maximum voltage here you can have? Right? So this point, right? If it reach VDD plus 0.7 volts, right? This diode will be turned off, right? So the current will all flowing through these diodes, right? So that means the maximum voltage for this point can only reach VDD plus 0.7 volts. It cannot be higher. Right? Great. So in this way, right, actually you can protect your device. Right? So if you don't have these diodes, right, this voltage here can be higher, right? Because of the inductor action here, inductive action here. Okay. So this one, you will see very common, right? Why you need a diode here, right? Usually it's for protection purpose. For protection purpose. Okay. And sometimes you will see an additional diode from here to ground. Right? So again, you look at this diode, right? For most of the time, you see when the voltage here is positive, right? This diode is always turned off, right? No use, right? Great. When this voltage is positive, right? This diode actually is no use, right? But if this voltage, right, can become negative voltage, right? So this diode actually will be turned off, right? Right? So when is you may ask me, right, why this voltage can be negative? Because I have a 0 volts here, you have a VDD here, right? Why your voltage here can be negative? So the voltage can become negative, right, when there is an inductor. There is the possibility, right, during the transit, right, this voltage can go to negative because of the inductor. Okay, so if this voltage, right, goes to negative, right, your diode here actually can turn on, right? This is negative, this is 0, right? So the current can go this direction. Okay. So the voltage here, right? Okay. So the voltage here, the minimum you can go is by 7 volts. Right? You cannot be lower. It cannot be lower, right? Because of the diode here. Okay. So this is some of the things you. I mean, these are the basic things for you to remember. So because I know you are the mechanical engineer, but some of these things you still need to aware. Okay. So for example, like the diodes, right, may be used for protection, right? If you are a circuit, etc. Okay. Okay. Next. So next we are going to discuss. Let's say you are motor, right? Can we have a current flow sometimes in this direction, sometimes in the other direction? So this is very common in the washing machine, right? So you know your motor, right? Sometimes you do in this direction, sometimes you need to spin in this direction, right? Especially during the washing, right? This direction, right? So if you want to have a different direction, basically the current need to flow in a different direction. In this direction, probably you rotate this direction the other way. Okay, so how do we control the current, right, to flow in both directions? We can use the circuit here called H bridge, right? So this one is look like a H, right? Like this, right? You have two MOSFETs here and two MOSFETs here. Okay. So at one point, let's say this MOSFET and this MOSFET turn off. This one turn on, this one turn on, right? Then you have a current flow from here program. Okay. At the other point, this MOSFET turn off, this one off, right? This one on, this one on, right? Then you have a current flow from VDD program in this direction. So if you compare these two cases, right, the current are actually flowing in different direction. Okay? Yeah. So how to control turn on and turn off of these MOSFETs, right? You can use microcontroller. Okay. So you can connect your Arduino, right, output, for example, right, to here to different things, right? Then you can write your own program to control transistors. Okay. Okay. So next, we want to discuss a little bit, right, on outputs. So earlier, right, we say the outputs, right, can only be 0 and 1, right, if it's from digital items, right? But let's say I want to get an output voltage, right, somewhere in between, right? Somewhere in between 0 and VDD, right? How should I do that? Right? So the most common way is we can use DAC, which is called digital to analog converter. So what is this DAC means? Right? Digital to analog. So basically the input is digital, output is analog. Once we have the analog output, right, basically that means we can have some value, right, in between 0 to VDD. And that's analog output, right? Okay, I'll discuss a few times before, right? DAC, right? So input is digital, output is analog, right? So that we can have the outputs, right, somewhere in between 0 and VDD. So how do we do that? So basically, we can use this formula, right? So let's say if you have a DAC, right? So your maximum value, let's say, for example, right? If it's 8-bit microprocessor, right? What is the maximum value, right? You say if it's 8-bit, right? The number basically is from 0, 0, 0, 0, 0, right? All ones, right? So what is the maximum value? So it's from 0 to 255, right? So for 8-bit, this is the range, right? 0 to 255. Okay. So if your digital inputs is somewhere in between, right? Let's say it's 1, 0, 0, 0, 1, something, right? So that gives you, let's say, a value of 100. Right? So you can use 100 divided by 255 times a certain reference voltage, right? That gives you the output voltage. Right? This basically is what DAC can do. Okay? It depends on your digital input, right? Your digital inputs, if it's 8-bit, right? So basically you can have any value, right? From 0, 0, 0, right, to 1, 1, 1, right? So any digital inputs value, right? Then depends on the input values, the DAC can produce the corresponding analog outputs for you. Right? So which is, so reference voltage, you can take it as a VDD. So the output from the DAC, right, basically is some value, right? Any value, right? Within 0 to VDD. So you get the point, right? Okay, but for most of the microcontrollers, right, we are going to use, right, we don't have DAC. We don't have a built-in DAC. So if you want to use DAC, actually you need to buy a separate DAC. Right? For example, like Arduino, right, you have used, right? We don't have DAC in Arduino board. Right? For any Arduino board, we don't have DAC. Okay? So if you really want to use, you need to buy. But then you might ask me, right? Then does it mean Arduino cannot produce any outputs which is between 0 and VDD? No, actually there are different ways to do that. So one of the common ways is what we call power width modulation. Right? So what is the power width modulation do is, let me jump a little bit, right? Okay, so if you look at the waveform here, right? So if you look at the second one, right? Second one basically is the waveform shows you the pulse, right? Is turn on 50% of the time the pulse is on, right? 50% of the time the pulse is off. So if you look at this waveform, right? What is the average voltage you are going to get? So the voltage, right, is from 0 to VDD, right? So if you have a pulse like this one, right? What is the average value you are going to get? Yeah? So what is the average value for this pulse? Yeah, anyone? It's half 0, half VDD. So what is the average value? It will be half VDD, right? That's average, right? And if you look at the first pulse here, so it has a very small turn on time. The rest are turn off, right? Yeah. So what is the average value for this case? So, okay, let me ask you. The average value for this, the average voltage value for this one, right, is close to VDD or close to 0? It will be close to 0, right? Yeah? And how about the last one? Right? The pulse actually turn on most of the time, right? Only a very small time right here is off. Right? So what is the average value for this pulse? So it will be close to VDD, right? So in this way, right, actually you can. So actually this is a very smart way to produce the output values, right, which are somewhere in between 0 and VDD. Right? Although the waveform here, right, is still digital, right? Because your waveform here, right, is 0 or VDD, right? It's still digital. But if you look at the average value, right, actually it's different, right? If you compare this one, actually it's from a small voltage value to the half VDD to the close to VDD, right? The average value actually is changing, right? Next I will show you the one program, right? You will see the difference here. Okay, so this one we call it we actually use the duty cycles, right, to control, to change the average power, right, delivered to the load, right. So what does the duty cycle mean, right? Duty cycle basically is the amount of time, right, the pulse is on, right? So when it's on, right, we say this is on duty, right? Okay. So when it's off, so it's off duty, right? So for the first case here, right? For the first case here, the duty cycle actually is low, right? Because the turn-on time is low, right? So your output voltage actually is low. For the second case, actually here is 50% duty cycle, because it's 50% on and 50% off. Right? So your average voltage value actually is half VDD. And for the last case here, because it's most of the time is on, right? So the duty cycle is close to 100%, right? 90%, 100%. So the average voltage value for this case will be close to VDD. So by changing the duty cycle, right, we can actually control the average voltage or average power delivered to the load. Okay, so now the next question you may ask me, right? If I use this kind of pulse, right, to control my LED, right? Okay, to control my LED. So I might notice, right, because for this part, my LED is on, right? For this part, my LED is off, right? So I can actually notice my LED is turned on and turned off, right? But actually, what happens is if your frequency is high enough, right, your eyes cannot notice the LED actually being turned on and off. If your frequency is low, you will see. And if your frequency is high, you only see the intensity, right, of the light, right, actually is changing. You will not see the light being turned on or off. This one actually is equivalent to, it's very similar to the movie. So for the movies, right, you see the continuous motion, right? But actually, the standard is what kind of frame standard we have? We have the 30 frames per second, right? Which is the standard for the movie, right? So for the movie itself, actually it's a discrete, but only thing because our eyes, right, our response time for our eyes, right, is only about 0.1 seconds. So that means if the number of frames per second, right, is large enough, right, our eyes can only see a continuous motion. Right? This is actually very similar to pulse width modulation here. Okay, let me show you the program you will see. Okay, so the program here, let me. is a very simple program, right? So now I think you all know, right, how it works, right? So I define a pin 10, right, as my output pin, right? So first I use the digital write, right, to write this pin 10 to high, right? So here, okay. So again, this delay, right? Now I don't use the delay function we used earlier, right? Now I use delay microseconds. So that means the number here, right, is in microseconds, not the milliseconds we used before. Okay. So what this program do basically is you turn on this LED for some time, right? Then you turn off this LED then for some time, right? Then this program, because it's inside the loop, right? So basically it will run continuously, right? So now let's say I change this turn on time, right? Let's say first I change to 10, right? So I change to 10, that means for every cycle, right? My LED only turn off for 10 microseconds. Then the rest of time is turned on. Right? So you see every cycle, right, actually is 100 microseconds, right? If you write the program like this, read it. So every cycle is every cycle is 1,000 microseconds, right? So that means what is the frequency here? So what is the frequency here? The frequency actually is 1,000 hertz, right?
Yes.
Yeah, good. So the frequency here actually is 1 kilohertz. So 1 kilohertz, if you do this way, right, you won't notice the LED is being turned on and turned off. What you can notice is only the light intensity is different. Because 1 kilohertz, right, is high enough so that our eyes, right, cannot notice it actually is switching. Okay? So next I want to show you, I want to connect to the Arduino board, right? I want to show you the difference. Let's say I change the number here, right? From 10 to 100 until to 900, right? Yeah. For example here, right? Until 900, right? So you will see the light intensity actually is changing, right? Although my program inside here, right, is switching on and turn on and turn off the LED. But what you can see is only the difference in the intensity, not the switching. Right? So this is the idea for the PWM actually. Yeah. So this part, yeah. So actually it's a very simple code, right, which can implement the PWM and pulse width modulation by changing the duty cycles. Okay, by changing the duty cycles. Okay, so in other words, right, the PWM can be implemented purely by codes. Right? Actually, you don't need additional hardware to do it. You can use the digital I/O, right? Then you can write the code to implement the PWM functions. Okay, so this one, right? Anything you can implement by software, right? Last time we have a term for it. What is that? Anyone still remember? So if anything we can implement purely by codes, right? What do we call it? We call it Big Bang. Big Bang. Okay. Big Bang. Yeah. So this actually is one of the questions, exam questions last year, right? Yeah. Yeah. So most likely this year won't come out today. Okay. Okay. Let me show you the Arduino one.
The one.
Okay, so the idea is very simple, right? So I just need to connect my LED, right? So once I connect to a ground, the other side connect to lambda 10. Right? So I need to connect my Arduino to the computer.
Dream of 19,500 copy that. Jadi I just stream scan.
Okay, let me start from the turn-on time is only 10 microseconds, right? So that means most of the time is off, right? So you can see, the light is very, barely you can see, right? Okay, now, let's say I change to 250.
What is this idea?
250 microseconds, right? So it's like the duty cycle is 25%. Okay, so now you will see the difference in the intensity, light intensity. Okay, so now this is 25%. 25%. So now if I change to 50% duty cycle, yeah, so increase, right? So again, the other point is, can you see the LED is blinking? No, right? Can you see the LED is blinking? Cannot, right? Because the frequency is high enough, you won't notice. Right? Because now my frequency is 1 kilohertz. Right? Our eyes cannot catch the blinking. Okay, next, this side I increase my duty cycle right to 90%. 90%. Okay. Yeah, so you can see some change, right? Light intensity here. Yeah. So of course, I mean, you won't see it very clear from the screen here, but there's some change in the intensity. Okay. All right. Okay, so now the idea for the pulse width modulation, right? So basically is you can control the duty cycle, right, of the waveform, right, square waveform, right? And so that you can change the average output voltage or output power. So how to generate the PWM waveform, right? Just now you see in the Arduino code, right? Basically, you can control your turn on time and turn off time, right? So again, the nodes here is old codes, right? And the idea is the same, right? You can see you want to turn on for one milliseconds and turn off for 1 millisecond, right? So for this example, basically it's a 50% duty cycle. So the idea is the same, right? The syntax we don't use it anymore. This is the old syntax. Okay, and of course, I mean we can use a program, write a program to generate the PWM, right? So if you read through these flowcharts, right, basically you can use your counter, right? The counter to control the turn on time and turn off time, right? For your waveform. Okay. Okay, so to generate the PWM, basically you need the counters, right? And for some of the microcontrollers, we actually have used the registers to do it. So basically, this is a different way to implement the PWM. So for Arduino just now, actually we have very simple way to do it. Right? You just control your on and turn off. The idea we show here, right? Example we show here, basically you have many different ways to implement PWM. Okay. And this one actually, if you want to use register, right? Actually it's a more robust way to do it. Okay. But it really depends on what you need. Okay, so what is the disadvantage, right, for PWM? So if your just now, right, we say if it's 8-bit processor, right? So we could have 256 possible values, right? Okay, so that means if you want to have a precise control, right? Yeah. You need to have 256 possible values, right? That actually takes time to do it. For example, let's say your microcontroller, right, need to execute the instructions every microsecond, right? So that means one period, right? You need 40 milliseconds to do it. Okay, which corresponds to frequency of 4 kilohertz. Okay, that actually is I mean it depends on the application. For some applications, right, this frequency actually is too low. Okay, so the disadvantage for PWM, right, there is a limit for the frequency that you can go. Okay. But again, for most of the applications, for many applications, right, yeah, this frequency is good enough. Right? For example, like a washing machine, whatever. Why do you need such a high frequency? Right. Okay. Next, I'm going to discuss the motor and servo a little bit, right? So basically, one of the main components, right, for the microcontroller you want to control is the motor or servo, right? Because you want to do something, right? You want to do the, for example, like a washing machine or something, right? So you want to control the motor movement, right? How do we control, right? And you know, for servos, right? For servos, so basically they don't turn continuously, right? Like a motor. They rotate their outputs, right, through a range of 90 degrees, right? So basically what it means is it can rotate. It's like a discrete motion, right? Okay. So to control the motors, right, you can use the pulses to control, right? So it depends on the length of the pulse, right? For example, like if the length is 1 millisecond, and this is your length of the pulse, right? if it's 1 millisecond, it will turn to the left by 45 degrees. Right? If it's the length of the motor is 1.5 milliseconds, right? It will stay in the center, right? If the pulse is 2 milliseconds, right? It will move to the right. Right? So in this way, actually, you can control the servo movement, right? By controlling the duration of pulse. Right? Again, this is very easy for the Arduino to do, right? If you want to implement using Arduino, right? It's very simple, right? So you just need to control the width of pulse, right? So if it is 1 millisecond, right? You move to the left, right? If it's 1.5 milliseconds, stay in the center, right? If it's 2 milliseconds, to the right. Right? In this way, you can control your servo movement. Okay? Okay, next one is the stepper motor. Stepper motor actually is the other very common one. So what the stepper motor do is, the motor, right? Sometimes if I ask you, you thought it's just rotating continuously, right? But actually, some of the motors you see actually is stepper motor. Because the movement is the movement can be so fine, right? You don't notice actually it's a discrete movement. Right? What it means is, let's say if we look at the stepper motor like this one, the simplest stepper motor. So what this stepper motor can do is, let's say you have a coil, right? 1, 2, 3, 4, right? You only have 4 coils, right? So at one moment, right, I only activate the coil 1. I only activate coil 1, right? So if I activate this coil 1, right, so basically I pass the current through the coil 1. So after the current is passing through the coil 1, right, you will have a north and south pole, right? The coil actually acts like a magnet. So once you have a north and south, right, so your motor here, right, need to align because of the magnetic field, right? So your motor need to turn, right, to align to this magnetic field, right? Do you agree? Huh? Just like a magnetic attraction, right? Yeah. Okay. Now, at next moment, right? So now I turn off my coil 1, right? So now I activate my coil 2. Activate my coil 2. So because now the coil 2 is activated, right? So your motor need to turn, right? To align to coil 2, right? Okay. So the next moment I turn off coil 2, right? Activate coil 3. Then your motor need to turn, right? Again, to align to coil 3, right? Then next, I turn off coil 3, turn on coil 4, right? So your motor need to turn again, right? So let me ask you, right? So every rotation, right? For this case, is how many degrees? So from 1, 2, 3, 4, right? From 1 to 2, 2 to 3, 3 to 4, right? So every rotation is how many degrees? Yeah? How many degrees? Every rotation. 45, right? Yeah? From 1 to 2, 2 to 3, yeah? Actually it's 45 degrees. Okay? So now, you actually have the other, you have more control here. Let's say if you want to activate 1 and 2, right, both at the same time. And both at the same time. So your motor right now need to align to the center, right? And because if you have a 1 and 2, right, both turn on, right? So you have a strongest magnetic field somewhere in the center, right? So your motor now need to align to the center here. Agree? Yeah. So in this way, actually, your rotation, right? Every rotation now is 22.5 degrees. Okay? Yeah. So now you see, if you have a motor, right, with more coils, spreading out this circle, right? If you have more coils, then you can have a final movement, right, of the motor. Do you agree? Yeah. So if you have a much more, now you have only 4 coils here, right? Yeah. If you have much more coils, yeah, you can have a much precise movement of the motor. Right? This is how the stepper motor works, right? Okay. So the typical value, right, for a stepper motor actually is 48 steps, which is 7.5 degrees. Okay. So this is what we have discussed, yeah, for the stepper motor just now, right? Yeah. We can actually, by combination, right? First, we can control the coil 1, next control coil 1 plus coil 2, right? Then coil 2, right? Coil 2 plus coil 3, right? So in this way, actually, the rotation can be 22.5 degrees. Okay, and this is the sum of the waveforms, right? You can use to drive the stepper motor, right? So let's look at one by one. Let's say for this case, right? At this point of time, right? The coil 1 and coil 2 are turned on, right? And this one, coil 2 and coil 3 are turned on, right? This one, coil 3 and coil 4 are turned on, right? And this one is coil 1 and coil 4 are turned on, right? So if you have the output waveform like this one, right? So you can actually control your motor movement, right? Do you agree? Right? So if it's a coil 1 and coil 2, right? So the motor need to align to the center of coil 1 and coil 2, right? Next moment is coil 2 and coil 3, right? Yeah, they move down, right? Coil 2 and coil 3. Yeah, this way, actually, the motor is rotating, right? So how do you control the coil 1, coil 2, coil 3, right? Let's say, for example, right? If you have 4 outputs from the Arduino, right? So these 4 outputs connect to different coils. Okay. So by writing the correct codes, right, you generate the corresponding waveforms from the different outputs, right? Now you can control your motor movement. Do you agree? Yeah. Okay. So again, to control the stepper motor, right? Yeah. So basically, you need to have the clock, right? And you need to generate the correct waveforms, right? To provide the correct movements. Okay. And if you want to drive the motor, basically you need to have the components we discussed earlier, right? It can be laminate pair or HC grid, right? That depends on the current which is required for the particular motor. Okay, so basically this one gives you the idea, right? Yeah? You can actually control the motor movement, using the microcontrollers. If you can have a program, right, provide the correct waveforms, correct outputs from the microcontrollers, and then you can control the motor movements. So if you need more information on motor, because motor is actually is a very big topic. Yeah. so many different types of motors available, right? Small, big, stepper motors, servos, etc. Right? So you can go to a different resources to find out what kind of motors you need, what kind of applications you need. And these are some information you can find. Right? And again, for the stepper motors, right, you have wide range of choices, right? And it really depends on your applications. You're going to segment. Okay, and of course, I mean the stepper motors are not the only motors, right? Just now I mentioned to you, the common one actually is DC motor, which can run continuously. But to control such a DC motors, right, then you need to have some special control mechanisms for that. And for stepper motors, you can use digital outputs, whatever, right, digital waveform to control. Right? But if it's a normal DC motors, right, which can run continuously, right, so how do you control the movement? Right? So you need to have some control mechanisms for that. Right? Okay. Then the other one is I want to mention to you is usually you cannot get very small stepper motor. Why is that? Because if you look at the stepper motor, right, inside, you need to have the small coils, right? Because of that, right, you cannot make your stepper motor very small. But because of those are small coils. Okay? So for the DC motor, actually you can get very small one, DC motor. Because inside the DC motor, you only have one circular magnet, right? Yeah. But for stepper motors, right? Yeah. Usually you cannot get a very small one. Okay. And also you need to remember, for most of motors, right, you need to supply a much bigger current, right, to make sure the current is sufficient, right, to drive the motor. Right. So all these things, again, you need to look at the data sheet. Right? What kind of motor you're going to use, what kind of current you need, then you need to design what kind of driver you need, whether you need a bipolar, you need Arlington, or you need a MOSFET. So it all depends on the kind of applications you are looking at. Okay? Okay, so these are some conclusions, right? So we discussed how to control the loads, right? So there are many ways to control. Right? You can have a bipolar, and you can use Arlington, MOSFET, etc. Right? And then what is the power space modulation? Right? We also spent some time to discuss it. Right? And also we have discussed how to control the servos and how to control the stepper motors. Okay. Okay. Next, I want to go through a little bit of the ADC. You know, what is ADC? So ADC basically is the analog to digital converter. Just now we discussed it's a digital to analog converter. Right? So for ADC is analog to digital. What it means is your input is analog, right? Output is digital. Okay. So let's see. That's ADC. Okay? Input is analog, output is digital. So ADC is a very common component we need for the microcontroller systems. Arduino it has its own built-in ADC. Why is that? Because you see, when the Arduino, right, for example, you connect to a temperature sensor, right? So the temperature sensor reads something, right? The data from the reading from the temperature sensor actually is analog, correct? Right? So when the Arduino is connected to the sensor, right? So you basically you taking the data right from the temperature sensor. So that data actually is analog. So you need ADC to convert this data into a digital data, so that Arduino can process it. Okay. So Arduino has its own ADC, right, which is analog to digital converter. So if you look at the diagram here, right? So actually our world, right, is an analog world. The digital world, digital actually is created by human beings, by our scientists. Right? Our world is analog, right? So you need the ADC to convert the analog to a digital data, right? So that your microcontroller, right, can process it. So after you process it, right, you need the DAC, right, which is the digital to analog converter, to convert it back to analog signals. So this is actually how it works. So this part, right, the center part, actually, I have said, right, the center part actually is created by our human beings. Because the reason basically is for the processing, right? Or because we need different levels of processing, right, for the signals. Right? So for that signal processing part, right, the digital signal is actually easier compared to analog signals. That's why for the digital signals, for the signal processing, right, we want it to be done in digital formats. But the real world actually is analog. So for the input signal, we need to convert it to digital, and then we need to have a DAC to convert back to the analog. Okay. So analog signal and the digital signal, we have discussed the difference before, right? So for analog signal, basically the data, right, can be anywhere between 0 to VDD. Right? The value actually can be continuous. The digital signal basically only 0 and 1, right? Okay? So that's the difference between the analog and the digital. Okay, so how can we convert the analog signal to a digital signal, right? So if you look at this example here, right? So if we have a sinusoidal input, sine wave, right? So this sinusoidal input basically is analog signal, right? Right? So because for this sinusoidal inputs, you have all the values, right? Like if you look at each point, right? If you look at each point, so the value can be any value from 0 to 1, right? For this sinusoidal inputs. Right? But if you want to represent this analog, the sinusoidal input using the digital data, right? So basically, you need to convert each point, right, into a corresponding digital data, right? So for this case, let's say we only want to use, let's say, only 3 bits. Let's say we only want to use the 3 bits to represent the analog inputs, right? Then the digital data, right, can only be from 000 to 111, right? 3 bits. Right? We just use it as a one example, right? So we want to represent the input value from 0 to 1 volt, right? Using 3 bits, right? Using 3 bits. Then your output, digital outputs, right, can only be from 000, right, to 111, right? But then if you look at your digital outputs, right, now you will have this kind of waveform. Right? It's not smooth anymore, right? Because now your analog outputs, right, you only use 3 bits to represent. Okay? So if you compare this analog signal, the sinusoidal input, right, with the digital inputs, right, the digital outputs here. If you compare the difference, you will get this kind of graph here. Right? This is what we call quantization error. Right? So basically, this is the difference between the analog signal and the digital signal. Okay, let me show you here, right? What is the meaning of quantization error? Okay, so if you have a sine wave, right? Okay, so from 0 to 1, right? The beta pi is 0.5, right? So if you have sine wave like this one, okay, this is your sinusoidal wave, right? Okay. So if you want to represent your sinusoidal input, right, using 3 bits, right? So that means your data can only from 0, 0, 0 to 1, 1, 1, right? 3 bits. Then you have 0, 0, 1, 0, 1, 0, right? 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. How many levels? Only 8 levels in between, right? Okay? So what it means is, so anything in between, let's say for example, right? Anything in between. So let me give you a scale here, right? Okay, the scale here is 1 to 0, right? But you only have 8 levels here, right? Okay, so you only have 8 levels here. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, right? And so on, right? 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, right? So from 0 to 1, you only have 8 levels, right? What it means is any value, right, from 0 to 0.125, right? Any value here, let's say you want to assign to 0, 0, 0, right? Yeah. Of course, here you have a choice. But let's say you want to assign, right, any values from 0 to 0.125, right, to 0, 0, 0, right? And from 0.125 to 0.25, right, any value here you will assign to 001. So now you see the issue, right? Right? Because your digital outputs here, right, you only have 8 possible values. Right? You only have 8 possible values. And you want to use these 8 possible values to represent any numbers in between 0 to 1. Yeah? So you see the problem, right? So if you only have 8 possible values to represent these values, right, you will have some errors here, right? So let's say for this case, right, your 0 volt is 0, 0, 0, right? But 0.1 volt is also 0, 0, 0, right? Right? And 0.11 also 0, 0, 0, right? Right? So if you use this kind of digital format, right, basically you cannot differentiate the difference between 0 and 0.1 volt, right? Right? So how can we solve this kind of the problem? One way is we can use more bits, right? Right? We can increase the number of bits to represent the analog signal here. Okay? So The higher number of bits, the better. Right? The better resolution. Yeah, that's the resolution we are talking about. Okay?
Very good. Good.
So again, so if your sinusoid, for example, in this case, right, if you only use 3 bits to represent, right, so you will see the error between the digital signal and the analog signal. It will be like this one. Okay. And next one, I want to quickly go through, right? And I think this one you did not do before, right? How to do something.